now. So we need to move beyond psychopathology, as this group would certainly support, and biological reductionism to an understanding of the structures of consciousness and the experienced world. Selfhood, temporality, spatiality, affectivity, and embodiment in relation to biological processes using an enactive interdisciplinary framework for explaining the human condition. So my talk today focuses on the embodiment of familiarity and trust, drawing from Dr. Tomasovic's book, Ecology of the Brain, and my recent book, The Mind-Brain Continuum, Psychoneurointrachronology, which presents an autopoietic theory and neuroendocrine model of the mind-brain continuum. In the time that we have today, I would like to give you an overview of this model. The synthesis and integration I developed is rich with interconnections that impact the experience of familiarity and trust, and the phenomenology and psychopathology of embodiment. However, the slides contain too much detail for the purposes of this overview, and so I encourage you to go back to review them for more in-depth understanding. I'm going to move the slide. Just
which button? Yeah.
this one. To this one? Or this one? Go back.
Oh, here.
Oh, use that?
Use the mouse and.
Okay.
Oh, yeah.
Okay, that's great. So which one?
Just touch the pad.
Touch the pad?
Yeah.
No, we want to go back to. Okay. Progression of ideas. So the progression of ideas begin with autopoiesis and enactive cognition and the mind-brain continuum, followed by a discussion of neurobiological mechanisms involving well-being, adrenal insufficiency, and stress integration. These mechanisms have explanatory value across age and gender, with the greatest point of visibility being women at midlife. So my lecture will focus there. I then conclude with the clinical implications of this model. So the Greek word autopoiesis combines auto or self with poiesis, meaning creation or production. Enaction refers to embodied action and lived experience. Cognition is the sense-making capacity of life as a form of embodied action. So a few definitions. So the theory of autopoiesis marked an evolutionary understanding of self-organization. The structural determinism of biological systems, chemical, neuronal, and cognitive, the emergence that produces life in its circular form, and the roots of human understanding. The foundations of autopoiesis in the philosophy of science and the neurophysiology of cognition first appeared in the work of Umberto Maturana and Francisco Varela in Autopoiesis and Cognition, the Realization of the Living. Maturana and Varela adapted principles from cybernetics and dynamic systems theory to formulate their theory of autopoiesis, which argues that living systems are endogenously controlled, self-organizing, emergent, autonomous, operationally closed, membrane-bound reaction networks. For example, the nervous system is not an input-output information processing system, but an operationally closed network whose elements are invariant patterns of activity in neuronal ensembles that function to create meaning, in which cognitive structures emerge from sensory motor patterns of perception and action. Knowledge is itself enacted. So, sorry about the. Okay. A cognitive being's world is a relational domain enacted by that person's autonomous agency and autopoietic mode of coupling with the environment. The organism's organizational structure gives rise to the processes of experience, development, and learning, which modify and in turn change their organic structure. Biological systems regenerate and transform themselves in mutual interactions through structural coupling, whereby the nervous system pairs sensory and motor surfaces through a network of neurons amidst a changing internal environment. Biochemical pathways of the cell and its membranes regenerate through the internal production of substratum components. Biochemical states of the organism transform the state of activity of neural networks by acting on the neuron's membrane receptors. In this way, the nervous system generates and maintains coherent and meaningful patterns of activity according to its operation as an organizationally closed, circular, sensory motor network of interacting neurons. However, the system's evolution, or the phylogeny of the organism, is a natural drift with no fixed point of reference. It maintains the conservation of autopoiesis and adaptation, permitting structural change of varied patterns within interneuronal networks. The concept of autopoiesis has been applied to cognition, systems theory, neuroscience, biochemistry, biology, and sociology. It has been used to describe biological homeostasis and the evolution of human societies. Varela, Thompson, and Roche's book, The Embodied Mind, stands in contradistinction to the received view that perception is the reconstruction of the physical world through the mind's registering environmental information. If we do not presuppose that an objective world independent of us as observers, everything is relative, and the problem of how experience is enacted or coupled to a surrounding world, resulting from our biological and social histories, is understandable. Human subjectivity, embodied as felt sense or consciousness of self, is a multidimensional stream of thoughts, perceptions, imaginations, representations, memories, and emotions. Consciousness is a distributed phenomenon of the whole active organism. As a product of the integration of organism and environment, it continually evolves while biological systems regenerate and transform themselves in mutual interactions through structural coupling. Cognitive processes are enacted through interdependencies with the environment from which meaning becomes inseparable. Biochemical states of the brain transform neural networks, and states of the nervous system change the state of the organism through its sensory motor coupling with neuronal networks. The emergent process of self-making is thus grounded in the processes that characterize lived experience, autopoiesis at the biological level, temporalization and self-reference at the level of conscious experience, and conceptual and narrative construction at the level of intersubjectivity. In Ecology of the Brain, Thomas Fuchs further argues that the brain alone is not constitutive for subjective experience. Conscious experience, when regarded as a byproduct or epiphenomenon of the brain's activity, separates the brain from the living body and the person's intentional interactions with their environment. Instead, he argues, the brain is a relational organ of the lived body and the physical body that mediates between aspects within the organism subject, between subjects, and between the subject and their environment. It is not creator of the mind in the experience world, but a mediating organ
No, it's correct. It's third bullet point. It's correct.
mediating organ.
The third bullet point.
The brain is not the brain.
Creator of the mind in the experience world, but a mediating organ that structures the mind itself.
Yeah.
Thank you.
Mm-hmm.
Structures of the mind is a plastic system of open loops formed from the integrated activity of the living being and are imprinted onto the brain. In this way, mind and brain form a reciprocal relationship between process and structure embedded in the relation between organism and environment. So applying the concept of autopoiesis to circular causality and homeostasis, Thomas argues that homeostatic cycles between the brain and body form the basis of pre-reflective self-awareness, basal state, or the feeling of being alive, which through interoceptive signals serving homeostasis are integrated by centers in the brain, stem, diencephalon, and hypothalamus. Circularity characterizes the structural dynamics of the organism, part to whole, and the processes of development over time. Between higher and lower level processes, the whole and its parts, we see macro and micro level reciprocal relations of self-organizing systems. A living being is a system that, why is this skipping?
There you go.
A living being is a system that reproduces its components, which regenerate the system as a whole. Downward, whole to part, upward, part to whole, higher to lower, and lower to higher. For example, in regulating emotional state, psychopharmacology has upward causality. The patient swallows a pill and it affects their brain, whereas psychotherapy and the intersubjective doctor-patient relationship has downward causality. It affects the integral level of organism-environment interaction top-down that feeds into physiological processes. Learning and development have a spiral nature. Conscious experience, feelings, emotions, and affect serves the biological homeostasis of the organism as a whole. Sensory motor cycles between brain, body, and environment are extended towards the world by the habitual functioning of the lived body, mirrored on the biological level by the structural coupling of organism and environment through circular perception action loops. Continuous incorporation of experience into body memory induces neuroplastic changes in the neuronal matrix and synaptic structure of neural networks. The connectivity strength between brain regions results in more adaptive patterns of neural activity. Over time, experience, habits, skills, interactive schemes, and dispositions that characterize an individual is sedimented in body memory. Interactive experience becomes an organic disposition, which enables new forms of experience as life processes lead to structural change. So, is there a mind-brain continuum? Psychoneuroendocrinology is a construct I developed that situates the paradigm of neurophenomenology and the embodied self at three levels: psychological, neurological, and intracrinological. Psychological refers to constructs variously referred to as psyche, self, soul, mind, and consciousness. Neurological to the composition of reactions within the nervous system. And intracrinological to the intracellular biosynthesis of steroids, the binding of receptors, and the formation of enzymes that catalyze the creation of hormones within the cell. Well, according to the natural sciences, the brain produces the mind, relegating consciousness to an epiphenomenon. Characterized by autopoietic autonomy, human beings are not reducible to the mental and physical events that constitute them. Reality is not given, it is perceiver dependent. So in this book, I explain how a woman's sense of self is biologically and energetically rooted at the confluence of the hypothalamic pituitary ovarian and adrenal axes, which regulate the biosynthesis of estrogens and androgens and the reactive anticipatory response to stress in states of attention, affect, and arousal at all levels of intracellular organization. This model has explanatory value, providing a way to bridge the gap between the mind and the brain, not only how the mind develops meaning and the sense of well-being, but ultimately how the notion of self emerges from this complex system. So in the table of contents in my book, part one, I focus on the critique of scientific, critique of scientific reductionism, foundations of the theory of autopoiesis, enactive cognition, the embodied mind, and models of the self and self-actualization. And in part two, it elucidates the neurobiological transition in women at midlife, endocrinology, and the psychoneuroendocrine hypothesis. Right. So what neuroendocrine factors contribute to the emergence of personality? The intrauterine environment provides the fetus with their first intersubjective, co-creative, consensual, organismic experience, imprinting maternal, hormonal, autonomic, and affective states during gestational bonding. The prenatal environment, conveyed through the placenta, sets the stage for the individual's disposition after birth and allows the fetus to survive the vagaries of stressful challenges prior to birth. The adrenal cortex, cortical hormones, the glucocorticoids, cortisol and cortisone, and the mineral corticoid aldosterone protect the developing person from situations that may cause profound pathological changes through the modulation of blood sugar, inflammation, and electrolytes. However, the fine-tuning of the function of the individual, the deeper within substrate, is managed within the organism intracellularly through the endocrine biosynthesis of not only adrenal steroids, but also the sexual steroids inside the cytoplasm. While the predominant amount of sexual and adrenal steroids in circulation are manufactured either in the gonads or the adrenal cortex, the modulation or fine-tuning of these functions is more effectively controlled within the cytoplasm of the cells that already possess the target receptors for these hormones. Endocrine biosynthesis is accomplished through the downregulation of DHEA, or dehydroepiandrosterone, and to a certain extent, the downregulation from progesterone. What is interesting about the environment within the cytoplasm of cells is that 75% of the active steroids that control the effects of the receptors are produced intracrinologically in the cycling female and in the male, and in the menopausal female. This is over 90% of the activity. Thus, it's important to understand the intracrine environment in terms of and reflected by the individual's psychological state or condition and their ability to find balance and equanimity within the external environment. The well-compensated individual who rarely relies on the stress response modulated by the adrenal cortex can be viewed to perhaps be more effective at modulating their own intracellular environment and intracrinologically synthesizing these hormones. However, as this function becomes more challenged by the dysregulating effects of aging and stress, and the resultant decrease in the biosynthesis of DHEA and progesterone, the internal environment becomes more challenged and dysregulated by external stressors. So in naturopathic clinical practice, we refer to this as metabolic syndrome or dysautonomia, which is associated with environmental allergies, food sensitivities, the gut microbiome, and nutritional deficiencies that often manifest psychologically as well as immunologically, with increased vulnerability to infection, inflammation, and chronic degenerative diseases. So the leading question, how is this related to the embodiment of familiarity and trust in midlife? So research on the so-called psychiatric mood and anxiety disorders, as well as phobias, neurotic obsessions, and also schizophrenia that occur in conjunction with reproductive transitions in women during menarche, perinatal, postpartum, perimenopause, and menopause, as well as normal fluctuations during the phases of the menstrual cycle itself, represent unique points along the lifespan for which a biological trigger, the change in the level of hormones, occurs concomitant with change in mood, affect, and arousal. Women at midlife typically experience an existential crisis of meaning and identity when the familiarity of their embodied state turns to distrust with somatic dysregulation of the menstrual cycle, autonomic nervous system, sleep-wake cycle, and with this, their felt sense of time. Pre-reflective states of self and mood that arise from hormonal, visceral, and affective dispositions involve the denial of death and the fear of non-being. Heidegger describes primordial absorption as an existential fear of being in the world and being towards death as constitutive of or intrinsic to the unfolding of meaning. In Jung's model, self-realization and psychic integration or wholeness arise through conflict and collaboration between consciousness and the unconscious as the self becomes the center of personality. Anthropological, intersubjective, psychosocial factors may also include a woman's perceived loss of femininity and motherhood, children leaving home, empty nest, caring for aging parents, and the search for generativity and personal authority. So what occurs in the at the neurobiological level? The beginning of a woman's reproductive life occurs at menarche. Neurobiological change derives from the complex interplay between hormones and peripheral circulation, neuropeptides, neurosteroids, and excitatory and inhibitory neurotransmitters, inflicting sympathetic and parasympathetic arousal. Concomitant change in mood, affect, and behavior are associated with the neuroendocrine regulation of the HPO, hypothalamic pituitary ovarian, and HPA, adrenal axes, and cortical subcortical control of the hypothalamic circuitry. During the reproductive years, the ovary has a cyclic function under the feedback control of the HPO and HPA axes. The HPO axis governs development, reproduction, immunity, and aging. The HPA axis regulates the fight or flight response to stress and homeostasis. The functional balance between hormone receptors at these axes depends on the need to maintain the menstrual cycle and the response to stress. The next few slides show an overview of these systems. So this is a flow chart of the mechanism of the HPO axis. Gonadotropin-releasing hormone, GnRH, signals the ovary to secrete estradiol and progesterone, which stimulates the anterior pituitary to secrete FSH, followed by a preovulatory LH surge, ovulation, a luteal phase, and menstruation. Okay. This graph shows hormonal change in peripheral circulation measured in plasma and serum during the normal 28-day menstrual cycle. Estrogen measured at estradiol increases in the follicular phase. Why is this skipping?
Your hand on the desk.
I'm on this. Autopoiesis, yeah, right.
Devices need.
Okay, so estrogen measured at estradiol increases the follicular phase and then slowly declines during the luteal phase. Progesterone is low during the follicular phase, then increases in peaks days 20 to 23. And then both estrogen and progesterone dramatically decrease on or about day 26 if there's no implantation, triggering the onset of menstruation, shedding of the endometrial lining. While FSH, LH, estradiol, and progesterone fluctuate rhythmically across the normal menstrual cycle, the equilibrium of hormones within this system depend on the phase of the woman's cycle, balanced by her need for progesterone synthesis to meet the demands of stress. So then what happens during perimenopause? Although estrogen and progesterone continue to sensitize receptors for each other throughout the cycle, when estradiol, which is normally bound to its receptor mid-cycle by progesterone, becomes deficient, circulating estrogen levels drop prematurely before the luteal phase begins. When this happens, estrogen is released from its receptor before adequate enzymes, which convert estradiol to estrone and estriol, are present. If this pattern becomes chronic, it can lead to a state of progesterone deficiency, relative estrogen excess, and adrenal insufficiency. So neurotransmitters as chemical messengers facilitate communication between neurons in the brain and nervous system to excite, inhibit, or modulate. Why does this keep skipping? Okay. Modulate physiological functions, including mood, emotion, stress, autonomic regulation, and cognition. This graph shows a rise in sympathetic nervous system activity in the late follicular phase after low levels of estrogen and progesterone, and a decline in serotonergic and GABAergic systems during the early follicular phase. So then at ovulation, with high levels of estrogen and low progesterone, the sympathetic system activity declines and the serotonergic system increases to prepare the woman for impregnation. During the mid-luteal phase, with high levels of both estrogen and progesterone, the sympathetic and GABAergic systems are elevated while the serotonergic systems decline. During the late luteal phase, with low levels of estrogen and progesterone, the sympathetic system retains its elevation while the serotonergic and GABAergic systems decline further. This graph shows the structural relationship between noradrenergic, dopaminergic, opioidergic, and GnRH neurons. This is the anatomical location, its importance, of the arcuate nucleus, median eminence of the hypothalamus, a circumventricular organ that creates a window for substances to cross the blood-brain barrier, where the modulation of pituitary function occurs. This graphic shows neurotransmitter control at the brainstem, the pons, medulla, and midbrain. Neurons secreting the neurotransmitters dopamine, acetylcholine, norepinephrine, and serotonin upward into the diencephalon and cerebrum and downward into the spinal cord modulate vegetative, basal, involuntary functions such as breathing, heart rate, blood pressure, sleep wakefulness, and temperature regulation. Now it's working. This is a flow chart of the HPA axis and the biochemical reactions associated with the anticipation and perception of stress. It's not working. Oh, because I touched this. The perception triggers the adrenal medulla to secrete dopamine, epinephrine, and norepinephrine, which signals the reticular activating system, a sensory pathway controlling the brain's excitability, to stimulate the hypothalamus to secrete corticotropin-releasing factor, CRF, which further produces corticotropin-releasing hormone, CRH. The neuropeptide CRF then integrates activation of the HPA axis by controlling the secretion of ACTH, beta-endorphin, and serotonin from the anterior pituitary and the adrenal cortex to secrete progesterone and DHEA, which increases the production of cortisol. Both reactive and anticipatory reactions are experience-dependent and autopoietic. This is a fascinating chart. It's more holistic representation of the steroid biosynthesis of sexual and adrenal steroids. So at the top of the chart are hormones synthesized from LDL cholesterol and pregnenolone. The same biochemical pathways are present in the ovary, testes, adrenal gland, and the brain by the same catalyzed enzymes printed at the bottom of the chart. So on the right side of the chart are sexual and adrenal steroids. Sorry.
Okay, yeah, you're good.
Synthesized from DHEA, estrogens, estrone, estradiol, and estriol, and the androgen testosterone. And on the left side of the chart are adrenal steroids synthesized from progesterone. So when the HPA axis is activated during stress, progesterone is down converted to its adrenal cortical metabolites, cortisol, which regulates blood sugar, cortisone, which regulates inflammation, and aldosterone, which regulates salt and water balance, blood pressure, and electrolytes. In a woman, DHEA initiates the menstrual cycle by its down conversion to estradiol in the ovarian granulosa cells mid-cycle via its metabolism to androstenedione. In addition to its contributions to the estrogens in ovulation, DHEA converted from DHEAS, its storage form, is synthesized by the adrenal gland and created de novo in tenfold quantity by neurosteroids in the brain, serving a role in the regulation of adrenal cortical function. Although at ovulation, DHEA's ovarian contribution to circulation increases to twice that of the adrenal cortex, it is synthesized by the adrenal gland throughout the cycle and serves a modulatory role in catalyzing enzymes, synthesizing neurotransmitters, and receptor sensitivity of neurosteroids. So due to the decline in DHEA with age and stress, we see a dramatic fall in the formation of androgens and estrogens in peripheral circulation as hormones are increasingly produced endocrinologically. And with prolonged stress, there's a depletion of DHEA so that less estrogen and testosterone are produced. So that when there is a demand on the body for DHEA reserves that it cannot meet, progesterone and 17-hydroxyprogesterone may be recruited to metabolize to estrogen via cross-conversion using the enzymes 17-hydrolase and 17-20-lyase, contributing to deficiencies in progesterone, adrenal cortical metabolites, and adrenal insufficiency. The term endocrinology was first used in 1988 by Fernand Lebris, professor of physiology and molecular medicine at Laval University in Quebec, to describe the intracellular synthesis and metabolism of hormones in peripheral tissues. Intracrine biosynthesis of estrogens, progesterone, and DHEA occurs as intracellular enzymes convert inactive prohormones into ligands, which activate receptors, modulating feedback from downstream or feed forward from upstream substrates. 75% of estrogens premenopause and over 90% of estrogens postmenopause are synthesized in peripheral tissues intracrinologically from precursor steroids of adrenal origin. This is fascinating. So in humans, endocrinology operates in each cell, in each tissue, involving tissue-specific local production and inactivation of sex steroids without release into peripheral circulation. Labrie argued that the inactive adrenal steroid DHEA is the most important precursor of bioactive androgens in women after the cessation of its ovarian biosynthesis. So we saw how DHEA initiates the menstrual cycle by aromatizing to estradiol in the ovarian granulosa cells mid-cycle via its metabolism to androstenedione. However, in addition to its contribution to the estrogens at ovulation, DHEA converted from DHES is synthesized by the adrenal gland, created de novo by neurosteroids in the brain, and serves as the source material for endocrine biosynthesis in peripheral tissues. The concentration of DHEA in circulation is progressively reduced from its peak at age 25 to less than 20% of that peak before the age of 70 in men and women. Therefore, endocrinology is an essential mechanism for maintaining homeostasis. DHEA is rendered active when the steroid sulfatase enzyme STS catalyzes the hydrolysis of sulfate esters to produce DHEA. STS is regarded as a fine-tuning mechanism for controlling levels of intracellular free steroids. In the brain, DHEA and DHEAS modulate GABA-A receptor, the NMDA receptor, and the sigma type 1 receptor. DHEA is also believed to interact with cytoskeletal components, novel membrane receptors, and receptor sites in the peripheral and central nervous system. Additionally, it modulates a variety of cholinergic, dopaminergic, and glutamatergic synaptic transmissions in which circulating bioavailable androgens and their precursors cross the plasma membrane of target cells to be metabolized by enzymes that are located intracellularly in the cytosol or endoplasmic reticulum. So my contention is that endocrine biosynthesis is autopoietic in the sense that the person's perception of experience and psychological state determines receptor sensitivity in response to local physiological need in both immediate, and stressful situations to fine-tune hormone receptor-dependent processes. During the fight or flight response to stress, additional DHEA is synthesized by the adrenal gland and created de novo by neurosteroids in the brain, serving a role in adrenocortical regulation, neurotransmitter synthesis, and receptor sensitivity within most cells. Progesterone is then down-converted to its adrenocortical metabolites, cortisol, cortisone, and aldosterone, to restore homeostasis in the sense of well-being. Peripheral tissue metabolism is thus a way in which tissues respond to local physiological demands and avoid systemic exposure to circulating hormones. So, in short review, the schematic illustrates how progesterone is used as a substrate to make estrogen and cortisol. Stress activates the CRH-ACTH pathway and the synthesis of cortisol. High levels of cortisol inhibit the synthesis of estrogen, LH, and GnRH, and further modulate progesterone's influence on CRH secretion from the hypothalamus to the anterior pituitary. So during perimenopause, hormone contributions from the gonads, the CNS, and the adrenal cortex fluctuate rhythmically and erratically until the establishment of a newer, equilibrated, lower level post-menopause. So we know that the HPA axis is keenly sensitive and refractory to fluctuation in gonadal steroids. And the mechanism of adrenal insufficiency applies to women throughout the lifespan. So I speculate that with the dysregulation of the HPO and HPA axis at ovulation, a stress-induced biorhythmic change occurs between the HPO-HPA axes in the medial preoptic area associated with the lymph projection system and the CRF-ACTH pathway between the paraventricular nucleus and the median eminence, which I'm going to show you shortly. Receptor sensitivity and enzyme titer modulate the endocrine biosynthesis of progesterone and DHEA to maintain the menstrual cycle in response to stress. Then with decreased enzymatic activity modulating receptor sensitivity, which controls the degree of activation or the hormone's effect, a steroid is less able to interact allosterically at a distance with the corresponding receptor's binding site and must rely on endocrine biosynthesis to restore homeostasis. With stress leading to insufficient progesterone at the midluteal peak, a woman may be unable to synthesize adequate glucocorticoids and mineralocorticoids, leading to a refractory chronic state of sympathetic hyperarousal, adrenal insufficiency, or the Chinese kidney yin deficiency. When a person experiences reactive stress, the HPA axis is activated. Reactive stress is a real threat to homeostasis and is recognized by somatic, visceral, or circumventricular pathways modulating change in cardiovascular tone, respiration, and visceral or somatic pain. However, HPA activation also occurs in the absence of primary sensory stimuli signaling homeostatic disruption and physiological challenge. This represents an effort by the organism to mount a glucocorticoid response in anticipation of, rather than in reaction to, homeostatic disruption. Anticipatory stress is generated by conditioning, sedimented in memory, or innate species-specific predispositions such as fight or flight with the recognition of a predator. Both reactive and anticipatory reactions are experience-dependent and autopoietic. Environmental stress associated with a reactive reaction can be itself conditioned, resulting in anticipatory response when the conditioned stimuli are next encountered. Coping with environmental or cognitive challenges by intrapsychically managing internal states of fear or anxiety is the autonomic nervous system's attempt to attenuate stress. So it's well accepted that the brain is a site of de novo synthesis, steroid biosynthesis. It is a steroidogenic organ akin to the adrenal gland, the gonads, and the placenta. Neurosteroids are generated by the same mechanisms but produced in the central and peripheral nervous system, either endogenously or from circulating sterols, and have a modulatory and signaling function. This graphic illustrates the synthesis of the reduced metabolites of DHE and progesterone in the brain from their sulfated storage form. This graphic shows the reciprocal interaction between the HPA and HPG, hypothalamic pituitary gonadal axes. This is fascinating evidence to support the idea that these axes as parallel processes that are continually influencing each other. It is believed that this co-regulation may occur through top-down activation and bottom-up feedback, and inter- and intra-axis communication as coupling of the HPA and HPG axes. I suspect that coupling may be derived through top-down involvement of social and emotional relevant circuitry, leading to parallel activation of these axes, depending on how an individual interprets their social context and sense of well-being. This graphic shows how the paraventricular nucleus receives sympathetic input from neurons, evoking rapid reflexive activation of the HPA axis. CRH neurons within the PVN stimulate the release of ACTH, which mediates the synthesis and release of corticosteroids from the adrenal gland. Regulated by sensory afferents, CRH neurons transmit reactive stimuli that are excitatory and direct. Limbic forebrain structures are believed to convey anticipatory signals that involve processing within pathways such as the peri-PVN and hypothalamic regions. However, integration of anticipatory circuits and neural pathways subserving reactive responses occurs at multiple levels. Let's take a look at that. So this graphic shows 5 limbic system regions known to affect HPA axis activation. None of these regions send direct projections to the paraventricular nucleus. However, all project to select brainstem, hypothalamic, and regions of the bed nucleus of the stria terminalis, or BST, that are known to innervate the medial parvocellular PVN. Limbic structures subserving anticipatory stress responses modulate PVN activation through interactions with stress circuits that mediate both reactive and anticipatory responses. This graphic shows the central mechanism of stress integration through projections to the medial PVN from 14 extrahypothalamic pathways regulating homeostatic functions. Projections are either GABAergic, open circles, or glutamatergic, closed circles. Hypothalamic nuclei subserving autonomic, metabolic, immune, and arousal signals from the arcuate nucleus, the median eminence, and the medial preoptic area. In addition to the bed nucleus of the stria terminalis, these regions express high levels of receptors for androgens, estrogens, and progesterone. So there's a cross-conversion within these fields of influence that are extra hypothalamic projections to the PVN. So a few clinical pearls. We know that sexual steroids that vary across the menstrual cycle influence neuronal activity and affective processing. Gut microbes communicate bidirectionally with the central nervous system via the vagus nerve, the immune inflammatory system, bacterial metabolites, neurotransmitters, the HPA axis, and yet unknown pathways. Estrogens regulate affective arousal via cortical-subcortical control through the hypothalamic circuitry and play an excitatory role in the CNS, increasing the sensitivity of the reticular activating system. Whereas progesterone, synthesized by the adrenal gland and the brain, plays a major role in the ability to stabilize nerve function and adapt to stress. As precursor of the glucocorticoids and the mineralocorticoid aldosterone, progesterone potentiates GABA in the CNS. In fact, chemically analogous to benzodiazepines, progesterone has anxiolytic, antidepressant, sedative, and neuroleptic-like effects as it shares properties with atypical antipsychotic drugs. Hormonal adequacy affects neurotransmitter synthesis, which affects sympathetic and parasympathetic arousal. The HBO axis are shown to play a role in the neurodevelopment etiology of schizophrenia. Menstrual cycle phase modulates prefrontal asymmetry. Fluctuant moods coincide with rapid change in ovarian steroids and the regulation of neurosteroids and neurotransmitters by monoamine oxidase. Mood and somatic symptoms show a phase-related increase in frequency of admission to psychiatric facilities in the late luteal phase. And the HPA axis is keenly sensitive to fluctuation in gonadal steroids. In fact, dysregulation in GABAergic transmission is emerging as a prominent theory underlying the etiology and perpetuation of stress-related psychiatric disorders. Excitatory actions of GABA have been demonstrated in both CRH neurons at the apex of control of the HPA axis and in GnRH neurons which mediate the HPO axis, adding complexity to the role of GABAergic signaling in the regulation of these systems. So in conclusion, don't do that. Change in the psychoneuroendocrine system arises from the complex interplay between the person's existential phenomenological state and neuroendocrine physiology and the adaptive response to stress, and the psychic emergence and integration of the self-actualizing dimension of personality. Enzymes of the sulfatase pathways for estrogen, progesterone, and DHEA as a circulating reservoir modulate the perception of experience and sense of well-being. Dysregulation of adrenocortical hormones due to stress diminishes endogenous reserves of DHEA and progesterone, which impacts the functionality of hormones, neurotransmitters, and neurosteroids, affecting the sense of self. Limbic projections to the PVN from the HPA axes modulate the stress response, integrating cortical, subcortical, autonomic, subliminal, and affective experience in the development of meaning. Cortical limbic projections along the SERA ACTH pathway, as we saw, and the convergence of gonadal steroids with the HPA axis in the medial preoptic area are an interface between the mind and the brain. The net impact of the stress response depends on the ensemble activity or global state of these fields of influence, within these neuronal projection systems. So my clinical experience using phenomenological interviews and craniosacral assessment in the context of psychotherapy enabled evaluation of the spatiotemporal structure and meaning of patients' lived experience, while a hormonal intervention of transbuccal DHEA, 5 milligrams per gram, and transdermal progesterone, 2.99%, was administered for 3 months. Clinical use of DHEA and progesterone supports the adrenal cortex and the integration of personality through the modulation of mood, affect, and cognition, impacting psychological equanimity, the sleep-wake cycle, and autonomic regulation. However, steroids are difficult to measure in blood, urine, or saliva because hormone species are transient, and sulfated and glucuronidated end products released into circulation are water-soluble and difficult to quantify. Whereas technological advances provide evidence of tissue-specific concentrations of steroids that do not parallel those in circulation, and increased understanding of enzymatic pathways that are regulated within the cell by selective down conversion for intracellular local action. Steroids are catalysts of infinitesimal concentrations, supporting and sustaining the evolution of human cells. It is their autopoietic capacity to transduce and transform that is the locus of an individual's energetic balance. Progesterone and DHEA deficiencies and HBO-HPA axis dysregulation are features of psychoneuroses and disturbance of the embodied self, but also the dialectic response compatible with a sense of well-being and the emergence of self as the boundaries of the personality are integrated. Thank you. I welcome your comments and questions.